Hey guys, this is Patrick from STH, and today we're going to take a look at liquid cooling. Specifically, we're going to take a look at three different types of liquid cooling. We're going to look at the rear door heat exchanger, we're going to look at immersion cooling, and then we're going to talk about direct to chip cooling. And then we're going to go a step further. We're not just going to talk about these different options, but we're also going to go take a look at what happens when you do that direct to chip liquid cooling. What are the gains that you get and why would you want to do something like that? So we're actually going to show an example using a very, very high-end system. Now, recently on STH, we've been doing a series looking at what's going to happen and what you need to know about servers, because there's huge amounts of changes that are going to happen in 2022 and beyond. We've already looked at things like EDSFF, CXL, large cache sizes, and all that kind of stuff. And we've also gone and started doing data center tours, so you can start getting some idea of all the operations and where all these technologies go into. But a big part of that series is really just the cooling side. I mean, the next generation of servers is going to use more power, and so we really need to get into liquid cooling. And in this video, we're gonna talk about why. So two quick bits of housekeeping here. First, you're gonna notice that this is not our normal studio. We recently did a video that not a whole lot of people watched, but did a video where we're actually moving the studio. And one of the big reasons that we're moving studio, one, we need more space, but then the second one is that we need to go and take advantage of liquid cooling in just our general testing. And so we needed to come up with a solution for that. And so the topic of this video is actually one of the reasons that we are moving the studio. Of course, it does not sound great. I'm not really happy with the lighting. I'm basically not really happy with this setup, but it is what we were gonna have, and we're probably gonna have this for another couple of videos as well while we're in this transitory period. The second one is that I came up with this idea a little while ago, and I really wanted to cover the subject because I think people are not really getting this message out there enough that liquid cooling is going to happen in 2022 if you want high density servers. And so I contacted a few folks, and Supermicro actually was gracious enough to set up the three different types in a lab just temporarily, so I could just drive over and take a look at them and show you guys what these look like. And not only do we have just the cooling solutions, we also had to have an 8 A100 NVIDIA A100 400 watt server, along with an 8 500 watt A100 server. The 400 watt one is air cooled and the 500 watt one is liquid cooled, and that's what we're going to show you a little bit later. That 400 to 500 watt transition is really a breakpoint in modern servers, and that's why I wanted to show those two different solutions side to side and actually give you a demonstration of what the difference is. And while that's today's servers, remember that the next generation of accelerators are going to go to 600 watts and beyond. So although we're right at that cusp of the breakpoint, this is where we're going to start to see that transition to needing liquid cooling happen in the next generations. So this is basically the setup that I needed to be able to show this breakpoint. So just being clear, we are going to mark this as sponsored, and the reason is that I just frankly we couldn't put this together ourselves, and I needed Supermicro to help out because they had all the stuff in their facilities, and I was able to just drive down and go take a look at it. But first, let's do a quick background on what's happening and why we're all talking about liquid cooling these days. So if we look to the 2022 generation of servers, we're going to start seeing, as I mentioned, 600 watt AI accelerators and GPUs. On the CPU side, we're going to see TDPs go over 300 watts. And what that practically means is that the servers that we're going to start to see in 2022 are going to go over about 1.5 kilowatts per U, and maybe even up to about 2 kilowatts per U. And what going up to those power levels means is that we're practically going to see data centers that weren't designed for those kind of high power and high heat output installations really start to struggle. And that's why the idea of having liquid cooling is actually, really an interesting one for a lot of folks, because there's the data center level, but then there's also just cooling the actual surface area of the chips at a sufficient rate. And although we have talked about this, especially when we did our Phoenix Snap data center tour video, what you will notice is that, liquid cooling and water cooling is actually really common in today's data centers, but that's really at the data center level. This next generation, and really if you want to get into that 40 kilowatts and higher per rack level, you're most likely going to have to bring liquid into the rack to be able to handle that kind of heat. So with that, let's get into some of the solutions that you might want to deploy. And I'm just going to show you what's out there, really talking about the basics of the rear door heat exchanger, talking about immersion cooling, and then direct to chip liquid cooling. Okay, the first solution that we're going to look at is the rear door heat exchanger. And just from a very high level, What this basically is a giant radiator and some fans that are attached to the rear door of a kind of standard rack actually. And the idea here is that you basically pump liquid into this giant radiator or heat exchanger, and then the hot air from a standard server goes through that radiator, and as it goes through the radiator, the heat is transferred to liquid, and that liquid is brought out of the facility so that way, cooling can happen outside of the data center floor. On this unit, and by the way, this is a little bit older of unit, really designed for more like the 20 kilowatt rack era. On this unit, you're gonna see that there are fans on the back of that, and there's monitoring solutions, all kinds of stuff that's going on to go regulate that airflow based on how hot the racks are. And what basically the idea is that those giant fans at the back are pulling air from the servers over the radiator, getting that heat exchange to happen, and then expelling air back into the data center as you normally would. Now, while the one we're looking at is really kind of in the 20 kilowatt-ish generation, the new ones can do over 40 kilowatts, and so that is something that people are investing in, and it is deployed at some very, very large organizations that are actually using this type of solution. One of the really big benefits is just the fact that you can still use your same vertical racks. You can use your same servers because the heat transfer basically goes, chip to heatsink to air out the back of the server, and then goes into this whole heat exchanger, rear door heat exchanger, and that's where that liquid is really brought into the equation. So you're not really changing the main servers or really most of your operations and stuff like that. You're just not making alterations to that, which makes it very easy to integrate relative to some of the other solutions. And just a quick little tidbit here, something I thought was pretty interesting is that there's actually I saw a little detection sensor, and there is a liquid or moisture detection sensor that you basically wrap around the fittings, because that's normally where you would see a leak, but also potentially the tubes and the pipes and whatever. And that is used so that if you do get some kind of leak, you'll have a detection and you can automatically shut down the server and make sure that you don't have something bad happen. So I know a lot of folks are gonna be really concerned about leaks, but not only do these like rear door heat exchangers, not only is there like a whole monitoring solution on that, but there's also a solution that is looking for moisture and stuff and trying to prevent a catastrophic failure. It was just something that I thought was interesting and I wanted to show you. Now, immersion cooling is kind of like the exact opposite. So if you just took the rear door heat exchanger as something that's relatively easy for your operations, the rear door heat exchanger, well, I guess you can integrate that very easily, but immersion cooling, I mean, that is absolutely a complete change to your data center and your operations. Instead of using vertical racks, you generally have horizontal bathtubs or tanks. Most people call them tanks. I've heard them called bathtubs a couple times, but the idea is that you have a giant vat of non-conductive fluid, and then you take your server, you dip your server into that, and the heat exchange happens from the chips and all the components on your server directly into that fluid. Now, there are a couple different designs on how these are actually implemented, and again, this is a little bit of an older generation that we're looking at, so there are new ones that Supermicro is deploying, but this is just like kind of what we could get kind of quickly and together, so that's why we're showing this one. But typically what you'll see is that you have that non-conductive liquid, and that fluid is actually very expensive, and there are reasons you don't want to have tons of it in your facility. So what you actually see is that often you'll have a heat exchanger that sits outside of the tank, and that heat exchanger basically will take the non-conductive liquid that's heated up and then pass it through the heat exchanger, will go to facility water, and the facility water will take the heat and bring that out of the, I guess, data center floor. And this solution is actually becoming quite popular because there are a number of benefits. Like number one, some folks have actually seen that you get higher reliability when you dip and you do immersion cooling, because air can have corrosive particles and what have you and properties to it, so you see like less corrosion and stuff like that with some of these fluids. And in fact, another really interesting one is that this actually became popular in some places, in places like China, where you have large population density at elevation, because your air density changes with elevation, right? Because when you're, say, on top of a mountain, you're not gonna have the same density of air that you have at sea level, and that means that you have less dense fluid, which means that you can't transfer as much heat in air, and so a data center that's air-cooled at elevation is not as efficient as it would be at sea level. So the immersion cooling kind of solves that problem, because you have a fluid that has a higher density and allows you to take more heat out. And so that was actually a reason that in China this became a, I guess, preferred solution for some of the higher elevation data centers. And another area, just kind of giving you an idea in terms of maturity, the early iterations of these immersion cooling tanks would just kind of use a standard server. You just dip the server in and let the thing go. But now there are companies out there that are actually looking at things like, if you have a heatsink, well, that heatsink is designed, your air-cooled heatsink is really designed for the fluid density of air. But if you have a more dense liquid, that means that you have different fluid dynamics. And so there are companies out there that are creating custom immersion cooling heatsinks that are designed to more efficiently move heat away from components in immersion cooling. So that's kind of cool and just kind of shows you how mature the market is getting. But as cool as immersion cooling is, and these things are people are already looking at doing 100 kilowatts and more per tank, there are some definite challenges. The first one is just the fact that most facilities that are out there are not made for horizontal tanks. They're made for vertical racks. And that presents some just basic operational challenges. So because you have a tank and a tub, right, where you have to basically only have access on the top because you have fluid sitting in there, it basically means that to put a server in or to pull a server out, you have to do that vertically. And that's totally different than pulling out a server out of a standard rack horizontally, right? So what you see is that not only do you have to have a different footprint just because the racks are horizontal versus vertical, but you also have to have things like hoists on the ceiling to be able to lift the servers out of the tub of fluid or just drop them in there, because a lot of servers are still pretty heavy and you have to basically lift them up sometimes a couple feet to be able, or meter or whatever, to be able to get them out of these tanks. And so you actually have to have things like hoists on the ceiling to be able to get them out of immersion tanks and be able to service them. And then there's other kinds of just challenges with the fluid. For example, when you have a server that's been dipped into an immersion tank, it comes out and it's probably covered in some film or maybe just some of that fluid that it was dipped in. And so you have to find some way to be able to clean components so you can actually go service the systems. Something that you'll probably have seen is just the fact that we had a large pallet tank from ExxonMobil, and they were the ones that made that fluid. But there's a whole bunch of different fluids that are being used right now. And it very much, I'm not talking about this particular one, but just in general in the industry, what you'll see is that some of them are actually toxic and can give off toxic fumes and stuff like that. So from an operational standpoint, there are people that are just concerned with the fact hey, well, can we really have something that could potentially, maybe not all the time, but potentially make a toxic fume and environment for our data center tech staff? I mean, that really would be not good. And so there are other ones that people claim are safe, and there's a whole wide range of performance and also those kind of environmental factors that go into the fluids, but that's still something that the industry is working on. Still, at the end of the day, the immersion cooling is really efficient, and people are getting over 100 kilowatts per tank or rack or whatever you would want to call that. And so they are able to cool a lot of the really high power stuff. And so if you want to get to a lot of density, that immersion cooling is actually a pretty interesting option. One piece of advice though that I've heard from a lot of organizations that have deployed these things so far is that it is a really good idea to go and get a server OEM along with the tank vendor and whoever all involved in a liquid cooling project, because there's just so much that has to change in your operational footprint that you just kind of need that. I mean, you're changing the hardware that's going in the tanks, you're changing the footprint potentially of your data center, and also the operation, so it's a big deal. All right, the third one is probably the one that most of you that are watching this are most familiar with, and that's really the direct-to-chip cooling. And so here what you basically have is you have liquid that is pumped to a cold plate that sits on a CPU or AI accelerator, GPU, something like that. And then that basically you do the chip to that cold plate to the liquid heat exchange, and then that liquid is brought out to some way to expel the heat out of the server. And this is very analogous to the kind of closed and custom loop systems that you see in workstations all the time these days. It's kind of the same idea, just scaled way up, because you're talking about way more power than you would have in a typical workstation. And remember, for one system, it may seem kind of easy, but when you start talking about getting racks of systems, well, that's when things get a little bit more challenging, because you have a lot more going on. And a really good example of that is that in these systems, in the racks that have these liquid cooling and direct-to-chip liquid cooling, you typically will have things like these just giant liquid or water distribution blocks, kind of like you would have a PDU on the side of your chassis or in a rack configuration, rack mounted configuration, but you have to have some kind of distribution to be able to manage all the loops. The systems that we're actually taking a look at, they're not just like a single loop per system. Oftentimes the AI accelerator systems will have to have multiple loops per system, and then there are multiple systems, so you just need a whole bunch of loops going on, and that's why you have these kind of distribution blocks. And there are a couple of different ways that these basically work. Now, one way is that you could actually take liquid or water and you take facility water, pump it through your rack and then out. And the idea there is that a lot of times your water cost is less than your power cost, and so it's actually a pretty inexpensive way to go do that. The other way that you'll see is that you'll see some kind of heat exchange happen, and that could happen either like in another rack or another part of the rack where you have a liquid to air and then that air goes out into the data center. The other way that you could do it is you could have a facility cooling solution or something like that. And so there are different ways that these are set up, but just kind of giving you an idea. The basic idea here is that you want to get that liquid going over a cold plate onto a heat source, whether that's CPU, GPU, AI accelerator. And the key thing there is that you're able to take heat away from that heat source fast enough that you can use higher power and hotter components. Then the question is just, what do you do with the different types of liquid and how do you get that heat, I guess, or handle that heat after it's been removed from the server? But there are different ways to go do that. Again, there are vendors that specialize in this. Still, this is perhaps the most mature and the one that I think most folks are really familiar with. And so what I wanted to do was do a test using the 400 watt and 500 watt GPUs and really kind of figure out and kind of show what the benefits are. And we figured out how to go do that. So for our test, what we actually had was 2 Supermicro servers, and these are 8 NVIDIA A100 GPU servers, the high-end GPU of today. We're actually using the AMD EPYC Milan versions of these servers. They can also support Rome as well. And then there are other versions of these servers that are also Intel Xeon Ice Lake servers. And so Supermicro has all those different options. We're just using the AMD versions here. Now in the air-cooled system, what we actually have is 8 400 watt NVIDIA A100 GPUs. Now, most of the vendors that are out there, like Supermicro, have the ability to cool 400 watt GPUs air-cooled, and that's really something that's kind of standard these days. But the other system that we have is actually the 80 gig 500 watt system. So the A100 80 gig 500 watt 8 different GPUs. And that's one where you start to see the fact that a lot of the vendors, depending on which vendor it is and all that kind of stuff, they really struggle to be able to cool that with air. I mean, there are some vendors that will put like 4 of those in a 4U system, and then they'll say like, hey, we can do air cooling, but if you have only 4 in 4U, then you can do air cooling as long as you keep your ambient temperatures kind of low enough in the data center. And so it's just a total mess. Like let's call it what it is. So a lot of vendors with these 500 watt GPUs are actually saying, yeah, it just makes sense to go to liquid cooling because we need to remove all that heat from those chips. And again, keep in mind that while we have, say, 270 to 280 watt CPUs and 400 to 500 watt GPUs in this test, what we're really looking at in the next generation is those CPUs are going to go over 300 watts, the GPUs are going to go over 600 watts, so we're going to start seeing another kilowatt or more per system, not even including any of the fans that you'd need to go and cool it. Now, what we actually did was we ran Linpack. And if you don't know Linpack, it's basically the high performance computing benchmark. It's been used for just years and years. It's not the best benchmark in the world, but it's also just something that's just so common in the industry. That's why we're using it. And a good example of how it's used is it's actually used to go and figure out what the top 500 supercomputers in the world are. And so that's kind of the benchmark that we're using. And it just so happens that a lot of those supercomputers use GPUs, so it works pretty easily. So the air-cooled system that we had actually used just over 5 kilowatts. And just remember here that we have 280 watt CPUs, we have 8 400 watt GPUs, and so getting over a little over 5 kilowatts is actually pretty common. And the difference, in case you're kind of doing the math and you're like, well, that's like 3.2 kilowatts worth of GPUs and a little over 500 watts of CPUs, that doesn't add up to over 5. The answer there is just the fact that it takes an absolute ton of fan power to be able to air cool a system like that. We have tested these 8 A100 systems from other vendors, and we saw similar power consumption over 5 kilowatts on those systems as well. So it is something that is just kind of standard in the industry. Now, the second system uses the 500 watt 80 gig NVIDIA A100s, and these are really the ones that most people say, yeah, you should be liquid cooling. And so there's a liquid cooling version of that. You can see on the front of the system that we have a number of loops that are there to be able to go and provide that kind of liquid direct to those chips. That way we can get more cooling. We have not just the loops on the GPUs, but also on the CPUs as well, because if you're gonna do it anyway, you might as well cool the CPUs as well. And basically what we got somewhere like that 20 to 25% more performance out of the system. And we were monitoring, and we did see the fact that the GPUs were going up to that 500 watt limit. So they weren't just stuck at 400 watts or anything like that. But we definitely did get more performance because we were using the higher power 80 watt GPUs. And when I say like, oh yeah, each GPU is using about 100 watts more, you're saying like, hey, there's like 8 GPUs, 100 watts more. So you should get about 800 watts more power consumption. But we actually only saw about 200 watts more than if we were using the 400 watt GPU solution. So it's 200 watts more, but we got like 20 to 25% more performance. And the reason for that is actually kind of easy. It's just the fact that the liquid is taking that heat away from those chips in a more efficient manner than if you're trying to blow fans over just copper or whatever heat sinks. Now, what's not included in that power consumption figure is like the water pumps and any of that kind of infrastructure. So there's definitely power that's happening, or power usage that's happening outside of the actual server that we're not including here. But just at the server level, it was only about 200 watts more, even though you would think it might be 800 watts or more because you'd spin your fans faster. And that, I think, really shows what the impact is, right? We were able to go up to that 80 gigabyte, 500 watt GPU. We didn't have to get stuck at that 400 watt level. So we were able to use the higher end GPUs. And you have to remember that these systems are over $100,000 each. So if you're getting 20% even performance, benefit from going to the higher power parts, and they're $100,000 systems, and you're talking about like, that's like 20,000 right there. Plus there are also density factors. Like for example, if you can fit more systems, you don't need to expand your data center footprint, or you can fit more systems in a given data center footprint. You can also do things like you can use DACs instead of optics for your networking, which you save money on that as well. And so there's a whole bunch of different costs that you actually, and an ROI calculation, you get more performance per system, plus you're getting, those density benefits, and that kind of really helps a lot on the ROI. And that's why folks, especially at the really, really high end, when you're starting to look at things like these AI acceleration or GPU compute systems, as well as things like the 2U 4-node form factors where you can get a ton of cores in a 2U system, those are ones that are really ripe for this kind of liquid cooling in this generation. All right, so let's wrap this up real quick, and let's just talk a little bit about the context, right? So the standard North American rack is a 208 volt, 30 amp rack, and that gives you, after this 20% safety margin, just under 5 kilowatts that's really usable in a rack. But what you'll notice is that the systems that we looked at today, they're all using more than 5 kilowatts. And then remember, in the next generation, we're gonna see even higher power components. And so what that really gets us to is just the point that to be able to move enough heat off of the components and handle a data center at that scale, you're gonna have to move to some kind of liquid cooling. That's just gonna have to happen, or else in the next generation, you're just not gonna be able to access the highest performing parts, and you're gonna have to go with less dense solutions. So the reason that we're doing this video is just because I want all of you on YouTube and our readers on the STH main site to be aware of the fact that this change is coming, and that you're gonna have to plan for that in the future. And that future isn't necessarily like really far away. It's not like crazy, 10 years in the future or anything like that. It's like literally a year or so away. And so I just really wanted to say thank you again to Supermicro for getting these systems, because this is really hard to kind of show all this stuff and be able to show that breakpoint between when you can do air cooling and when you need liquid cooling. So just want to say thank you again to Supermicro for making this happen and helping out with that. And hey, I know we're not in a normal studio. This is really rough to be filming in this versus that really great setup that we used to have. So just give it a little bit of time. One of the big reasons we are moving is to be able to handle not just a bigger studio, but then also be able to do some of this liquid cooling stuff, because we're going to need to do that in 2022 and beyond. And hey, if you like this video, why don't you give it a like, click subscribe, turn on those notifications so you can see whenever we come out with great new videos. As always, thanks for watching and have an awesome day.